This is the 22nd video in a series devoted to ordinary differential equations. Now, last time we looked at some systems of differential equations, systems of first-order linear differential equations, I should say, and we restricted ourselves to a special case. So let's recall what that special case was. So let's suppose we have numbers, lambda 1 to lambda n, which are all real, and they're eigenvalues of a matrix A, which is an n by n matrix. Then their corresponding eigenvectors are v1 to vn, and they're linearly independent. So what does that mean? That means that A gives us a basis for Rn out of its eigenvectors. So in other words, there's a basis of Rn made up of the eigenvectors of A. But that's exactly the condition for A to be a diagonalizable matrix. So it's really important to keep that in mind. Not only is it diagonalizable, but it's diagonalizable over the real numbers. Okay, so in that very special case, the differential equation given by vector function y prime equals a times vector function y is this. So the most general solution is given by the following formula. So I should say that if you have an initial condition, there's a little bit more work to do, but as long as you don't have an initial condition, this is our most general formula. We have vector function y is equal to c1 e to the lambda 1t times v1. So this is a scalar function times v1. So this is like a scalar function pointing in the direction of this first eigenvector, if you will. And then you'll add similar objects up to cn e to the lambda nt vn. So that's another scalar function in the direction of vn. Then we did some examples here, but essentially what this boils down to is finding the eigenvectors and eigenvalues of a matrix that's diagonalizable over the real numbers. So that actually means that we're missing two very important cases. And we're going to look at those cases today. So the first case is, what if the matrix is not diagonalizable at all? And then the second case is, well, what if it's diagonalizable but only over the complex numbers? And I should say that there's something general going on here using the matrix exponential, but we're going to stay a bit away from the matrix exponential just for the purposes of the course that I'm teaching. Maybe in the future I'll go and add some bonus videos to this playlist regarding how to do this generally with the matrix exponential, but we won't do that just now. Okay, so as a leading example, let's consider the following differential equation, or really system of differential equations if you think about this out into components. We have the vector function y prime equals the matrix 11, negative 25, 4, negative 9 times the vector function y. So we'd like to start by hoping that this works, but as we'll see, it will not. So let's find out our eigenvectors and our eigenvalues. So we'll need the characteristic polynomial. So let's just call this matrix A. PAX will be the determinant of x times the identity matrix minus A. Okay, so that's going to be the determinant, which is of x minus 11, 25 goes here, negative 4 goes here, and then x plus 9 goes here. And I'm using these vertical lines to mean take the determinant. Okay, so let's multiply this out. This will give us something like x squared, and then we'll have minus 11x plus 9x. So that'll be minus 2x, and then minus 99. But let's notice we have to add 100. So that'll be plus 1. So that gives us x minus 1 quantity squared if we were to factor it out. So that means we only have a single eigenvalue, and that eigenvalue, which I'll call lambda 1, is 1. Now immediately, since this is a 2 by 2 matrix, we know that this is not diagonalizable, because the only diagonalizable 2 by 2 matrices with only a single eigenvector are multiples of the identity. That being said, let's go ahead and calculate the eigenvector, because we'll use that kind of at the end of this whole process. So let's recall, in order to calculate the eigenvector, we'll look at the null space of lambda 1 times the identity matrix. So that's just going to be 1 times the identity matrix minus A. So minus our matrix A. So that is the null space of, let's see what we have. This will be minus 10 goes here, 25 minus 4, and then plus 10 goes here. Now let's divide the second row by 2 and this first row by 5. And recall that row operations do not change the null space. So that'll give us minus 2, 5 here, and minus 2, 5 here. But check it out, those two rows are the same, which means we can subtract one from the other. Again, that's a row operation which does not change the null space, giving us negative 2, 5, 0, 0. So we're finding the null space of this matrix. But that means we've got a system of equations to solve, which is minus 2x1 plus 5x2 equals 0, meaning that 5x2 is equal to 2x1. So we might as well take x1 to be equal to 5, which tells us that x2 is equal to 2. So one of those is a free variable, so we're fixing one or the other, and it's forcing the value of the following one. So that means this lambda 1 eigenvalue has eigenvector v, I'll call it v1 maybe, which is 5, 2. But notice we only got a single eigenvector there. We have an eigenvalue and a single eigenvector. But in order to use this rule over here, we need a basis of eigenvectors for R2, which means we need 2 eigenvectors. But we've only got 1 eigenvector, so that's a problem. We can't use this rule over here. So we've got to think up a different way to solve this. Well, let's maybe collect this eigenvalue, which I'll call lambda now, and this eigenvector, which I'll call v, up at the top, and then we'll hack together a solution from some stuff that we know about second order differential equations and see if we can relate that solution back to this eigenvalue and this eigenvector. So via some exploration, we just saw that our previous method did not work for this system of differential equations. So we're going to hack together a solution based off some stuff that we know already and try to put that system or try to put that solution in terms of this eigenvector eigenvalue relationship up here. Because hopefully there is still some sort of relationship for the final solution to those two objects. So now let's rewrite this vector differential equation as a system of differential equations. That means we'll have y1 prime is equal to 11y1 minus 25y2. So that's assuming that vector y is equal to components y1 and y2. And then likewise, we'll have y2 prime is equal to 4y1 minus 9y2. Great. And now I will rename y1 just plain old y, but not vector y. So let's do that. So let's set y equal to y1. And since we're aiming for a second order differential equation, we'd like to look at y double prime. And this is using something which I've been calling the rank order correspondence for differential equations. So in other words, the system of two differential equations that are first order corresponds to a second order differential equation and vice versa as well. Okay, so let's calculate y double prime. So notice that's the same thing as y1 double prime, but now we know y1 prime is this 11y1 minus 25y2, so that means we can set this equal to the derivative of this right-hand side using linearity. So that'll be 11y1 prime minus 25y2 prime. But now let's recall that y1 prime can be rewritten as just plain old y prime based off that notation. And then next, y2 prime can be rewritten using our second differential equation. So that'll be 4y1, which we might as well write as 4y minus 9y2. Okay, so let's collect and see what we have so far. we have y double prime equals 11y prime, and then minus 100y. So that would be from this 25 times 4, and then plus 25 times 9. I'm going to write that as 9 times 25y2. But what I'll do here is take this y2 and replace it using this first equation right here. So notice that this y2 is in fact equal to 1 over 25 times 11y1 minus y1 prime, but we might as well like rub out those ones given our kind of setup right here. So since the 25 here is built in, it'll cancel the 25 that we have over here, and we might as well write this as 9 times 11y minus y prime. And now we've got an honest to goodness second order differential equation for y. So now let's move some things around. So we'll have y double prime. Let's move the y prime stuff over. But notice we've got 11y prime minus 9y prime. So that gives us 2y prime. Moving it over is negative 2y prime. And then we have 100y and 99y. The 100 is negative, so that gives us negative y. Moving it over, we get plus y equals 0. But now let's look at the corresponding polynomial. So the corresponding polynomial here is r squared minus 2r plus 1 equals 0, which has r equals 1 as a double root. So since r equals 1 is a double root from the theory of second order linear differential equations with constant coefficients, which we already did, we know the general solution is y equals c1 plus c2 times x times e to the x. Okay, but now let's recall that y was really equal to y1 based off of this up here. So that means that we have a solution for y1. y1 is equal to this object right here. So that'll be c1 plus c2 times x times e to the x. But now looking ahead, we'll also want y2, which has this 1 over 25 built in. So we might as well like pull a 25 out of C1 and C2 by renaming C1 and C2. So what I'll do is instead call y1 25 times C1 plus C2x times e to the x, where really I've just like renamed C1 as like 25 times C1 or something like that. Those are arbitrary constants, so that's totally legal here. Okay, so what will we need moving on? Well, I'm going to need this description of y2 in terms of y1, and I'll need this solution down here for y1, and then we can start putting this solution together and hopefully making it look like something to do with this eigenvector-eigenvalue relationship. So far, for our system of differential equations, which is equivalent to the matrix vector differential equation, we found out that y1 was 25 times the quantity, c1 plus c2 times t, e to the t. I'd like to point out that I was using x as the independent variable on the last board, but that was like really a bit of a typo because we're doing everything in terms of t here for these systems of differential equations. So I've replaced it back there. That's not really a huge deal though. Then we have y2 is equal to 1 over 25, 11y1 minus y1 prime based off this first differential equation. Okay, so that's good. So now we'll use standard derivative rules to take this expression for y1 and put it inside of our equation for y2. So maybe I won't work out the details here because it's just really straightforward calculation, but here's what you end up with. You'll end up with y2 is equal to 10 times c1 plus c2t times e to the t, and then minus c2 times e to the t. So we end up with something like that. Okay, now let's actually move that up here so we've got plenty of room to finish it off. So now we're ready to finish this thing off. So we've got y vector is equal to y1, y2, but we know y1 and y2 by our previous calculation. So that'll be something like this. We have 25 c1 plus c2 times t times e to the t. But in fact, what I'll do is, since everything is a multiple of e to the t, I'll factor that out. And then down here in the second component, I have 10 c1 plus c2 times t minus c2. Good. And now what I'd like to note is that I've got stuff in terms of c1 and stuff also in terms of c2. That motivates us to pull this into two parts. And then I'll also pull out a 5 when possible. So that'll give me 5 c1 e to the t, and then I'll have 5 2. So that's going to be everything related to this constant term right here, this c1. Okay, then let's see what we have for this portion of the c2. So again, I can pull a 5 out, and that'll give me plus 5 c2 times t times e to the t, and then we'll have 5 2 again. Okay, so that's pretty cool. And then what do we have left over? Well, we're going to have minus c2 e to the t, and then the vector 0, 1. So something like that. Now I'm going to do one last thing for simplification. I'm going to change my constants, and here I'll actually change my constants, with a name or whatever, just to like keep it really simple. And what I'll do is I'll call 5c1 plus 5c2 maybe b1, and then I'll call negative c2 b2. Okay, and so that's because I can factor quite a bit of stuff out of this 5c1 plus 5c2, as they're both attached to e to the t, and they're both attached to this same vector. So let's note that we can now write this as, let's be careful about it. We have b1, so that's our constant, and then 1 plus t times e to the t times the vector pointing in the direction of 5, 2. And then we've got plus b2 times e to the t times 0, 1. So now I think it's pretty clear where part of these things come from. So notice the e to the 1t came from the fact that we have this eigenvalue of 1. This 5, 2 is our eigenvector, so that's good. Now we just have to figure out what this 0, 1 is. But we don't quite have room, so let's do that on the next board. So we got the final form of this matrix vector differential equation as follows. So it's b1, 1 plus t, e to the t in the direction of 5, 2. Notice that 5, 2 was an eigenvector of our matrix corresponding to eigenvalue 1. The number 1 shows up as a coefficient of t here. And then it was b2 times e to the t in the direction of 0, 1. So we understand where this vector came from. It's the eigenvector. Now we need to figure out where this other vector comes from. So this is a bit tricky. So it really is something related to this thing called the generalized eigenvector. And like even more generally, this is related to something called the Jordan canonical form of a matrix, but that's a little bit outside of the scope of what we want to do here. So what I'll do is instead is notice the following relationship. So if we take A minus the identity matrix and we multiply it into this matrix 0, 1, something interesting happens. So A minus the identity matrix has the following form. So we'll have 10, negative 25, 4, negative 10. And then, like I said, multiplying this into 0, 1 gives us the vector minus 25, minus 10. If we factor a scalar multiple of minus 5 out, we get 5, 2. Let's notice that 5, 2 is a multiple of our eigenvector up here. So what does that mean? Well, that means that in fact, if we So instead of multiplying 0 by a minus I, if we multiply it by a minus I squared, well, the first a minus I will take us here, but then recall that 5, 2 was in the null space of a minus I, so the second a minus I will take us to the 0 vector. So that's what makes this 0, 1 something called a generalized eigenvector. The fact that some power of a minus I takes it to the 0 vector. But that, like I said, that's kind of outside of the scope of what we want to do. The important thing here is that this extra vector that we have here satisfies this relationship that when we multiply it by this a minus I, which really a minus lambda times I, but lambda is 1 in this case, we get a multiple of our eigenvector that we have. Okay, so now that being said, let's summarize all of this over here and we'll do an example. So here's the big theorem that ties together some of the things that we observed in the last example. So let's suppose that A is an n by n matrix. Let's also suppose that it has an eigenvalue lambda, which is a real number. So let's point that out. It's a real number. And it has an algebraic multiplicity bigger than or equal to 2. So when I say algebraic multiplicity, I mean that it is at least a double root of the characteristic polynomial. But let's also suppose that it has a geometric multiplicity of 1. So by a geometric multiplicity of 1, I mean the eigenspace is one-dimensional, so it's spanned by one vector. And let's say that eigenvector is V, which is a vector in Rn. Then that implies, and this is from a theorem from linear algebra, that there exists a W in Rn such that A minus lambda I times W is equal to V. And this W is something called a generalized eigenvector like we saw before, and that's because if we multiply this again by A minus lambda I, we'll get 0. So in fact, A minus lambda I squared times W equals 0. Okay, then given that big setup, a solution, notice I'm saying a solution, not the most general solution, but a solution to the vector differential equation y prime equals a times y is given by the following combination of functions. We have c1 times 1 plus t e to the lambda t in the direction of v, this eigenvector, and then c2 e to the lambda t in the direction of w, this generalized eigenvector. Okay, so there's a lot of work to do here whenever you have one of these solutions. So let's look at this example. So we've got y prime is equal to this 3 by 3 matrix, 0, 2, 1, negative 4, 6, 1, and 0, 4, 2 times y. And I won't calculate this. In fact, you should be practiced up on this from the previous video, but you can calculate the eigenvalues are 4 and 0. Furthermore, the eigenvalue 4 has algebraic multiplicity equal to 2. But it has a geometric multiplicity of 1, and its eigenvector, which I'll call V1, is 1, 1, 2. Now, lambda 2 equals 0 has algebraic and geometric multiplicity 1, so that has eigenvector V2, which you can calculate to be negative 1, negative 1, 0. So in order to finish this thing off, what we need to do is find the corresponding W vector. So that means we need to solve the following matrix vector equation. So it'll be A minus 4 times the identity matrix, because it'll be this eigenvector or eigenvalue right here, times a vector W, which is to be found, equals V1. Okay, but let's notice that we can very easily put that into an augmented matrix form. So over on the left part of the augmented matrix will be A minus 4i, which turns into minus 4, 2, 1, minus 4, 2, 1, and then 0, 4, minus 2. And then over on the right part of the augmented side, you'll get v1, which is 1, 1, 2. So this is just basic linear algebra stuff here. Then, how do you solve this system of equations? Well, you'll do a row reduction. So I won't do that. Again, we are up to practice on that from the previous video. But doing row reduction gives you the following reduced row echelon form of this system. So we've got 1, 0, negative half, 0. And then we'll have 0, 1, negative half, and then half, and then a whole row of zeros. So we have something like that. But then if we introduce the notation W equals x1, x2, x3, then that corresponds to the following system of two equations and 3 unknowns. So we'll have x1 minus half x3 equals 0. That comes from the first row. We'll have x2 minus half x3 equals half. That comes from the second row. And then x3 is a free variable. That's because it's associated to a non-pivot column. So the fact that it's a free variable means we might as well take it to be equal to 0, which means we get x1 is 0 and x2 is half, meaning we have W is equal to 0, half, 0. Okay, so that's good. But now if multiplying a minus 4i to w gives us v1 in this form, we can scale this by 2 to the vector 0, 1, 0, and we won't achieve v1, we'll achieve twice v1. But that's okay because any multiple of an eigenvector is also an eigenvector. So needless to say, we might as well take w to be this right here. Okay, so from all of this information, we're actually ready to write down our general solution. So our general solution will have the following form. So we'll have vector y is c1, 1 plus t, e to the 4t, and then we'll have the vector 1, 1, 2. So that'll be associated to this eigenvalue. And then we'll have plus C2 times e to the 4t times this generalized eigenvector, which will be 0, 1, 0. And then we'll have plus C3 times e to the 0t, but e to the 0t is simply 1 times this eigenvector. So that'll be negative 1, negative 1, 2. So notice that we got these first two portions of our solution by our theorem over here. We got this third portion of our solution by stuff that we did last time. That was when the algebraic multiplicity and the geometric multiplicity matched. Okay, so this is good. Maybe I'll leave you with a warm-up problem now. So I'll leave you with a warm-up problem, and that would be vector y prime equals 3, 1, negative 1, 1 times vector y. So this will be one of these non-diagonalizable ones that we saw today, and that's a good place to stop.